Welcome to our podcast, Artificial Intelligence, Papers and Concepts. I am Jack Malik, your AI-generated host, and with me is my AI-generated co-host, Sophia Lane. This podcast is based on material curated by Dr. Satya Malik. Today, we're diving into something that's really stirred things up in the AI community, Andrej Karpathy's nanochat project. It's open source, and, well, the promise is pretty bold.
Right. It's basically a roadmap for building your own ChatGPT-like model, but minimally full stack, start to finish.
Exactly. So our mission here is to figure out how Karpathy pulled this off, making it so efficient, and why everyone's calling it this great learning tool for, people wanting to build AI.
Yeah, and what's cool is it's not just code, it's the whole process. He calls it a minimal, from-scratch, full-stack training inference pipeline of a simple ChatGPT clone. The key words there are minimal and clean.
Dependency light, hackable. Sounds ideal if you actually want to understand what's going on under the hood.
Precisely. If you want to see how everything connects from handling the raw text all the way to the chat window you type into this is kind of the blueprint.
Okay, let's hit the big headline first. Accessibility. We always hear LLMs cost millions, need huge server farms, but Karpathy talks about a speed run. How cheap, how fast are we talking here?
It's honestly pretty remarkable. He literally made a script called speedrun.exe. You run it, and assuming you've got access to a decent GPU setup, the example uses an 8x100 node, you can go from 0 to a working conversational AI in about 4 hours.
4 hours? Seriously?
Yeah.
And the cost?
That's the kicker. Around $100 in cloud compute costs for that whole run, maybe a bit more depending on pricing, but yeah, $100.
Wow. Okay, compared to the millions we usually hear about, well, it's a different league entirely. A game changer for learning, definitely.
Yeah, it just lowers the barrier so much.
But let's be real for a second. $100, 4 hours.
Yeah.
What kind of model do you actually get? The source material itself mentions things like naivety and hallucinations, right?
Yeah, and Karpathy is very upfront about that. This isn't going to beat GPT-4, not even close. It can do basic chat, answer simple questions, maybe write a little poem if you ask nicely.
But it acts like a kindergarten child, as they put it.
Sort of, yeah. It can get things wrong, make stuff up. It doesn't have that deep world knowledge or reasoning power yet. Its value isn't peak performance, it's the educational transparency.
So the point isn't the final model's genius, but understanding the whole journey to a model.
Exactly. It demystifies the process. You see the entire stack, tokenizer, training scripts, the inference engine, even a basic web UI all working together. And it's all done in roughly 8,000 lines of pretty clean Python and Rust code. It shows you the mechanics.
Right, understanding the plumbing, even if the water pressure isn't super high yet.
Yeah.
Okay, that makes sense. Let's unpack that pipeline then. 5 stages, going from just raw text to a chatbot. Where does stage 1 kick off?
It starts efficiently with tokenization. To make that 4-hour speed run feasible, they needed something fast. So Karpathy built a custom tokenizer in Rust.
Rust, not Python.
Right. It's a byte pair encoding tokenizer, BPE, with a decent vocabulary size, 65,536 tokens. Using Rust makes it GPU fast, way faster than standard Python libraries for this step, which really helps speed up getting the data ready for training.
Ah, so optimization starts right at the beginning with how you chop up the text.
You got it. Speed matters from step 1. Interestingly, though, while they use this custom Rust tokenizer for the training part, for the inference part, when you're actually chatting with the model, they often switch back to OpenAI's standard tick token library. So it's like bespoke speed for training, proven reliability for chatting.
Clever. Okay, so text is tokenized. Stage 2.
That's pre-training or base training. There's a script, script-space-train.py. This is where the model just reads a ton of text. Think massive web scrapes like the FineWeb EDU dataset they mentioned, all shuffled up.
And the goal here is just raw language learning.
Yep. Learn grammar, facts, how sentences work, general world knowledge. Basically, learn what language looks like.
Okay, so it knows language, but how does it learn to converse, do the back and forth thing?
That's stage 3, mid-training. Another script, scripts-midtrain.p. Here, they shift gears. They start feeding it conversational data. They mention small talk as an example. And crucially, they introduce special chat tokens.
Like user and assistant.
Exactly those. And also stop tokens, like assistant end. These teach the model the structure of a conversation, who's talking, when to respond, and importantly, when to stop talking so it doesn't just ramble on forever.
I remember reading about a little hiccup here, something about the learning rate schedule in this mid-training script, a bug they found.
Oh yeah, that's a good point. There was an early gotcha with the learning rate decay. It highlights that even in these minimal systems, tiny details in the training setup can really matter. Getting that fixed was key for making the conversational fine-tuning actually work well.
Shows how sensitive these things are. Okay, so pre-training, mid-training, what's next?
Stage 4 is supervised fine-tuning, or SFT. You take the conversationally aware model and polish it further using high-quality, curated examples. Think question and answer pairs. This really helps align its behavior to be more helpful and follow instructions better.
And there's an optional stage after that, RL.
Right, optional reinforcement learning. They use a method called GRPO, which stands for Generalized Policy Optimization. This isn't always needed, but they found it was really effective for boosting specific skills, particularly math problem solving, like getting better scores on the GSM-8K benchmark.
Why RL specifically for math? Couldn't SFT handle that?
SFT is good for style and factual recall from examples, but complex reasoning, like multi-step math problems, benefits from the model getting feedback on the final answer. RL methods like GRPO let the model try things out and get rewarded for correct solutions, which helps it learn those step-by-step reasoning paths more effectively than just seeing examples.
Okay, that makes sense. So SFT for general alignment, RL for targeted skill boosts, and the final stage.
Stage 5 is just inference, running the model you've trained, either using a command line tool or the simple web interface they provide, which is scriptchatweb.py. And that's the whole sequence, start to finish.
Got it. Tokenize, pre-train, mid-train, SFT, maybe RL, then infer. Okay, now for the really juicy part for tinkerers. Let's look inside the machine. What are the core code files defining the actual model architecture?
Right. If you want to mess with the code, there are 3 main files in the nanochat directory you absolutely need to know.
Okay.
First is nanochatgpt.py. This is the transformer model itself, but it's surprisingly concise. And it uses modern high-performance components, even though it's minimal.
Like what?
Things like RMS norm instead of layer norm for stability, rotary positional embeddings, which helps the model handle sequence length better, and efficient attention mechanisms like multi-query or grouped query attention, MQA or GQA.
Hold on, GQA. Isn't that usually for massive models to save memory during inference? Why put it in a nanochat?
That's actually a really smart choice. GQA drastically cuts down the size of the key value hash needed during inference. This means faster generation and lower memory use, even for a smaller model. It helps make the $100 speedrun actually produce something reasonably quick and usable, not just theoretically possible.
So the advanced features actually enable the minimalism to be practical.
Exactly. Oh, and one other slightly unusual thing in GPT.py is the activation function, ROU. Literally just f_relu x.square. Simple, effective nonlinearity.
Interesting. Okay, so GPT.py is the model brain. What handles making it actually talk?
That's nanochatengine.py. This implements how the model generates text, and it does it like a production system would. A 2-phase process. There's pre-fill, where it processes your initial prompt really fast. Then there's decode, where it generates the response token by token streaming it out.
And that decoding part needs to be efficient, right?
Yeah, absolutely. The key here is KV caching. Engine stores the calculated keys and values from previous tokens, so it doesn't have to recompute them every single time it generates the next token. That's essential for low latency streaming.
Makes sense. Anything else special in the engine?
Yeah, one really cool thing, tool use. The engine is designed to watch for special tokens. If the model outputs, say, Python start, the engine pauses generation, calls an actual Python interpreter in a safe sandbox to run the code the model generated, gets the result, and then lets the model continue. It lets the model use calculation tools.
Wow, okay. So it can actually do things, not just talk about them. That's pretty sophisticated for a minimal setup. And the third key file?
That would be config.py. This is basically your control panel for experimentation. Want a deeper model, change end layer, more attention heads, adjust end head, bigger embeddings, tweak nemd. It lets you scale the architecture up or down easily without digging deep into the GPT.py code.
Nice. Okay, let's circle back to that simplicity idea.
Yeah.
You mentioned they deliberately avoided using a padding token. Why is that such a big deal for simplifying things?
Padding. It's a common headache in LLM training. See, you usually train on batches of sequences, but sequences have different lengths. To make them fit neatly into a batch, you often add padding tokens to the shorter ones.
Right, just fill up the space.
Yeah, but then you need complex attention masks to tell the model, hey, ignore these fake padding tokens. This adds code complexity and can actually waste computation on the GPU because you're processing tokens that don't mean anything.
So nanochat doesn't do that.
Exactly. It avoids padding entirely. It relies on careful batching, attention masks that only cover the real data, and those special tokens like assistant tend to signal clearly where generation should stop. It strips out that whole layer of complexity.
That's a neat trick. It sounds like the whole thing is really designed to be easy to modify and scale then. If I wanted to take this and, say, train it on my company's internal documents,
should be relatively straightforward. Scaling the model size is mostly about changing that depth parameter in the config and maybe adjusting the device batch size if you hit memory limits. The scripts handle the gradient accumulation automatically to compensate.
And the data pipeline itself, is it locked into specific formats?
Nope, that's another area they kept simple. The nanochat dataset.py file intentionally avoids heavy, complex dataset libraries. It's designed to be simple to understand and modify. If you have your custom data, maybe as Parquet files like they use, swapping it in should be much easier than with some bigger frameworks.
Less abstraction, more clarity. I like it. What about reproducibility? That's always a challenge in AI. How do you know if your changes actually improved things?
They thought about that too. There's a nanochat report.py script. After a training run finishes, it automatically spits out a report.md file.
A report card, basically.
Pretty much. It logs everything. Your environment details, the exact hyperparameters you used, key performance metrics like core score, MMLU accuracy, that GSMAK math score. It makes comparing different runs much more reliable because all the context is saved automatically.
That's really valuable.
Okay.
So wrapping this up, nanochat sounds less like a competitor to giant models and more like an incredibly clear, functional, and affordable teaching tool.
I think that's exactly it. Its success isn't about raw power, but about providing that complete, understandable end-to-end stack. And maybe, just maybe, it poses a bit of a challenge to people building much bigger systems.
How so?
Well, it makes you ask. All those incredibly complex optimizations and exotic techniques people add to giant models, are they always worth the trade-off? Do you lose too much clarity, too much of that hackability that nanochat really champions? Sometimes being able to easily see and change every gear in the machine might be the most valuable feature you can have. It's definitely something to think about.
Thank you so much for listening. This podcast was sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. See you on our next episode.